Good morning, everybody. Welcome to 6046, 18410, and SMA 5503, Introduction to Algorithms. This is a course that is going to be taught both here at MIT and simultaneously at the National University of Singapore as part of the SMA, the Singapore-MIT Alliance. I'm going to be lecturing the course with Professor Eric Demain and Professor Lee Wee-sun, who is in Singapore and will only be lecturing to the Singaporean students. Okay, so everything that we're going to be doing this term is going to be done both in Singapore, which is currently on a 12-hour time difference from us, and here. So it's going to be very interesting. It's the first time I've done anything like this, and this is a big program at MIT. Has anybody else been involved in classes that have been taught in SMA here? No, so this is going to be interesting for everybody. Okay, but one of the things that's the case is that there's usually probably somebody awake who is dealing with the course. So, okay, so Eric, you can have a seat. I want everybody to take a look at handout 1. There are 5 handouts that we have prepared for class today. It gives the staff, the lecturers, and we have 5 teaching assistants for the MIT students. And the recitations will be taught by teaching assistants, and the SMA lecturer, Professor Lee, will teach the recitations in Singapore. Lee Deacon is our course secretary. We have a worldwide web page, which I encourage everybody to bookmark and make it convenient. And you can always reach us at 6046 staff, and that is always better, generally, unless it's something of a personal nature, than contacting an individual person. I don't want people saying, well, I emailed my TA and nobody responded for 3 days, and so therefore, no, you can email 6046 staff, and we will make sure somebody responds. Okay? So the distance learning program has 2 components to it. The first is that the lectures themselves will be videotaped. And so each time that we're here, they'll be videotaped. And then they will be synced up with online materials, lecture notes. And those materials will be available in Singapore hopefully by midday on the day after, because they're 12 hours ahead of us here at MIT, which corresponds to midnight tonight. They will be online. And MIT students also have access to those materials. And you may find that if 9:30 a.m. is too early for you to get up, that you can actually take the course, except that you're going to be behind by 12 hours. Now, in Singapore, that's okay, because they're going to delay their recitations and everything by a similar amount. But here, we're going to assign things and expect that you have received them at the same time in the lectures. So, so you can take them, not attend lecture and just use the online lectures, but in some sense you do so at your own risk. The prerequisites for the course are a strong understanding of programming and a solid background in discrete math, including probability. So if you have not had this material, you're not ready to take this course. We will be assigning a diagnostic exam this week, which is due in recitation on Friday. It's basically a 1-hour exam that is designed to test whether or not you have had the requisite background. And also, there are questions on there that are from this course material, so that I can judge how much of this material people have been exposed to before arriving in the class. When you do it, you're not supposed to go off and try to solve the problems and look things up in books and so forth. You just solve it off the top of your head. It doesn't count as part of your grade. Okay, it's just a diagnostic. But it is a requirement, because your registration is not complete, and you will not be registered for the class if you have not completed a diagnostic. Okay? Let's see. Lectures. You're responsible for material presented in lectures, including oral comments made by the lecturer. Recitation. There are recitations each week. Part of the registration is for MIT students. We'll be asking what your recitation preferences are. Okay. We will not any assignments for the MIT students which have been done by the registrar are no good. Okay, we will assign the recitations. The SMA students will be registered automatically, so there's no need to register. So they need to go to the sign-up sheet. All of you need to go to the sign-up sheet sometime today before 7 p.m. on the course web site and get registered. Most of the handouts will be available on the course web page. Although we brought handouts today to get you all started, generally the handouts will simply be available on the web and you can print them from there. Okay, we will not be providing hard copies generally. We will announce by the course mailing list when handouts are available. So you must pay attention to your email, which you will be entering in your registration information. The textbook. In previous terms, we have used this textbook. This textbook is no longer being used. So if you have this textbook, if you just bought this textbook, take it back. It's no good. We're using this textbook. It looks kind of similar, okay, because it is kind of similar, but it's different. This is the second edition, just completed. This is the first edition. First edition is like, you know, the computer you used when you were in high school. Okay? We're using the new modern computer because it has all the right stuff in it. Okay? So get this one. Generally, for MIT students, one of the things that you can do is obtain in the phone book, the MIT phone book, there are coupons for discounts at MIT Press. Get 20% off. This is an MIT Press book. You can go to the MIT Press bookstore, get a discount. Okay? So you can compare the prices. My observation in the past has been the prices at Quantum Books, at the Coop, and the MIT Press are generally different. Okay? And in my experience, you can't necessarily tell which one is going to be the cheapest. Okay? So shop around, and if people know, you should share it with your friends. Please go to the course website. Also, from the course website, you'll be able to get access to the videos and lecture notes. Extra help is available. There's the recitation instructors all will have office hours, and in addition, the MIT students have a variety of tutoring services that you can take advantage of. You can read about that. For registration, as I mentioned, you must go to the website and register today by 7 p.m. Otherwise, you won't be in the course. Okay, so 7 p.m. tonight. That should be plenty of time. Is there anybody here who cannot make it to a computer to register by 7 p.m. tonight? Very good. Okay, probably the people who aren't here, right? The SMA students do not need to register. You'll be registered automatically. We're expecting 9 problem sets during the semester. They typically have 2 or 3 problems on them, depending upon whether, if there's a holiday on 1 week, we have 3 problems going over 2 weeks. If there's not a holiday, then we have 2 problems in the 1 week. That's generally the strategy we use. The actual due dates are on the problem set itself, but I try to keep pretty close to what's in the tentative calendar. Generally, late homeworks are not accepted. If you have extenuating circumstances, you should make prior arrangements with your recitation instructor. Please do your problems on separate sheets of paper. Okay, one set of pages for each problem. Don't put the same problem because they may be separated for grading. Make sure that when you write up your homeworks that you identify not only the common information on the top of page 5 of this handout, but also the people you worked with on the problem, because we'll talk about collaboration in a minute. But the general policy is that you are free to collaborate on homeworks. Okay? Homeworks are designed to help you learn the material. And so if you don't know the answer, you should be collaborating in study groups or otherwise. Okay, what I'm asking for here is that you say who it is that you talked with about the preparation of this homework. Okay? And if none, then I want to see explicitly that you did not collaborate with people. Okay? But if you collaborated, it will not affect your grade in any way to say you collaborated with people. Okay? We just want to sort of keep track, and we also want to promote intellectual honesty as one of the core values of this particular class. Okay? You should be as clear and precise in your write-up of solutions, and understandably is as desirable as correctness. It's always, if you make it easier for us to grade and understand what you're doing, one, you'll pick up your own bugs more easily, okay, and therefore get more credit because you'll discover problems yourself with your arguments, okay? You'll be able to do sanity checks and so forth. And the other thing is that graders have this funny tendency to have a more positive attitude in awarding points when they can actually read what the problem says. So please be good. I think it's a good idea generally to copy over your problem sets. I know not everybody has a time to do that, but in my experience, doing things like that actually saves you time in the long run, okay, where you do up your notes and then you copy over what your final solution is. The problem set includes exercises that should be solved but not handed in, and you'll be responsible for the material in those exercises. I'm going to skip over the describing algorithms. I want you should read that. We are not going to get to actually describing algorithms in the first problem set particularly. So, but I want you to read that, and we will, especially in the latter half of the course, is really focused on design. Okay, so. So at that point, I wanted to have that in the outline. The grading policy. We basically have problem sets, one in-class quiz, one take-home quiz, and a final. Okay? And I give the relative points. The main thing I want you to understand is this table here about what the impact is of failing to do homework in the class. So homework has a relatively light impact on your grade. It's only 80 out of, I don't know what, almost 500 points or something. Okay? 500 or 400? 400 points. No, 500, I don't know. 400 to 500 points, somewhere in there. So, but the problems are essential for mastering the material. Okay? And so, if you don't skip any problems, it doesn't hurt your grade at all. That's the good news. Okay? If you skip one problem during the term, that's not a big deal. 1/100th of a letter grade you lose. Okay? That's not bad. That's only if you were right on the borderline, right? 1 point away from, B plus to A minus, right? Okay. 2, now it's 1/10th of a letter grade. Okay, so that's a typical problem set. Okay, 2 problems in a problem set. Okay, so it's 1/10th of a letter grade. Only the people who are reasonably close to the margin is that going to affect. But now we start to have real impact. Now, these are not problem sets. These are problems. Okay? By the time you've missed like 6 problems, you've lost half a letter grade. Okay? By the time you've skipped 7 problems, you've lost a whole letter grade. Then you lose 2 letter grades, then you fail. Okay? So it's pretty obvious from this that if you don't plan to do the homeworks in the class, you shouldn't expect to pass. Okay? So the idea is do the homeworks. Now the homeworks, as I say, you can collaborate on. You must write them up yourselves, however. Okay, individual write-ups. I don't want copying of one person's homeworks as another, handed in as another person's. But solving the problem, no problem. Okay? Collaboration policy. Any question about that, the grading policy? Is that pretty clear? What the impact is? Collaboration policy. I encourage you to collaborate, as I've said. I encourage you to form study groups. Okay? People who join study groups tend to do better than people who try to sweat through it alone. Okay? I recommend, however, that if you do join a study group to spend, half an hour to 45 minutes or so on the problem, each problem trying to solve it yourself before you go to your study group. Don't go to your study group expecting to have other people feed you the answers. You're not holding up your end of the bargain there. Okay? You try to solve the problem. Okay, if your group is unable to solve a problem, you can go talk with other groups, or you can talk with your recitation instructor. Okay? So I do encourage you to collaborate. However, you must write up each problem solution by yourself without assistance, even if you collaborate with others to solve the problems. Okay, if you didn't work, you have to write collaborators none on the top of your homework when you hand it in. Okay? If you decide that you want to do more research on this and it's really bugging you and nobody seems to be able to give you the answer, not even the recitation instructors, which I think will be unusual because they are a very sharp bunch of people. Actually, the recitation instructors, can you guys stand up so people see your faces? Here we go. Okay. Okay. Got to get some rise out of you guys. You all have been like, boy, it's early in the morning after a vacation. Very tough. Okay. So anyway, if you're not able to get answers, you can start looking on the web and you can, dig things up. Now, that has some problems because one of the policies I have in terms of running the course is trying to come up with a large number of fresh problems every term. Okay, so they're not going to be just canned problems. Some of them will be canned problems, but they will be the exception, not the rule. Okay, we make up a lot of new problems every term. Now, you can collaborate as much as you want on problems, but you can't collaborate on exams. There's always one or two people every term who somehow think that collaborating on exams is an accepted policy of this course. Okay? Collaborating on exams, it may sound straightforward, but I got to put it down, is not permitted no matter what. In particular, we have a take-home exam in this class where you're given the exam and have 4 or 5 days to solve the problems on it. Okay? During that time, and I'll be more explicit when we come up to that particular exam, no collaboration whatsoever is permitted. Okay? So, if during the term, during an exam or at any other time, you feel that you may have violated this policy, you say, or you're not sure where the policy is or whatever, you're not sure if you did something, please come talk to us. It is always more painful for a student when we find out from a third party that he or she has been violating the terms. This includes the policy of saying, well, he's my really best friend, and I'm just going to share with him because he's in trouble in this course. That's not how you deal with a best friend. If a best friend needs that kind of help, what he needs more than that is some counseling by one of the counseling deans, okay, or in MIT Medical in the mental health program. Okay? That's not what he needs if what he's doing, he or she is doing, and prevailing upon you to share information. Okay? That's not what they need. What they need is good counseling at that point, because somebody who's in that position is under a lot of stress, and MIT and the SMA program are going to be places where people feel a lot of stress. Okay? You need to make sure that they have proper ways of doing it and aren't so tied up in the things that are going on that they can't make sense between the difference of right and wrong. Okay? We'll talk more about this now. Now, this course has great material, so I want to get into it. Okay? And so it's really possible to have a tremendous amount of fun. We're going to try to do things like programming contests and things like that during the term. We're going to have a lot of fun in this class. It's great material. Okay, absolutely fantastic material. I love teaching this stuff. Okay, any questions? Everybody understands the rules? Okay, any questions, you can always email the staff or me or come talk to us. Good. So let's get going on content. Topic of this course is analysis of algorithms. Okay, it is the theoretical study of computer program performance. And other types of resource issues. And in fact, even it being computer program performance, you could even call into question. It's bigger than that, because people use it to determine how you build computer hardware, okay, and so forth. Okay, but the real focus of the course is on performance, making things run fast. Okay, now, what everybody thinks, because this is a class on performance, that performance must be important. Okay. I have done 25 years or more of engineering, okay, and performance is not the most important thing. What are some of the things that are more important in an engineering environment than performance?
Reliability.
Reliability, there's a good one. What's that? Maintainability. Modularity. Correctness. Very good. Correctness. Cost. Good. More? I made a long list here. Excuse me? Clarity. Yep. Simplicity. Excuse me? Size. Meaning? Simplicity. So the program size, you mean? Yeah. And there are other ones. Extensibility. Can you add on? What other ones? Robustness. You know, how much other stuff does it do? User friendliness. Okay. Etc. And I'm sure you can come up with a whole bunch of things. So then why do we bother to study this? We just talked about all these other things that are more important than performance. Why do we bother to study this? Okay, I'm starting out telling you that this stuff is just not at the top of what you should be concerned about when you're an engineer. Why do we care about this?
Because the better performance you have, it makes certain problems possible as opposed to impossible.
Yeah, that's a really good one. Okay, feasibility versus infeasibility. Often performance tells you what you are capable of doing. Why didn't we have computers capable of video 10 years ago? Not enough performance. Okay? So performance often draws the line between the feasible and the impossible. So for entrepreneurship, a lot of work is done near that line. And if you have a way of making something be a little bit more efficient, you can have an edge on your competition in what you can actually sell. What other reasons do we study performance?
Idea of the
Scalability. That's very good. Boy, it's like you have my notes. Did you guys? I put this up on the web last night. So did you guys start downloading my notes? No? Okay. Okay, scalability. That's good. Okay. And in fact, actually, scalability is pretty much what we're going to be talking about. So what often happens in an engineering environment is you design something, test it, everything works, it's got all the properties we talked about, user friendliness, reliability, etc. And then things get bigger, and the more users, okay, and larger database, and it grows like this and it breaks. Okay, very common problem. Okay, and one of the ways that it breaks is it used to be that you could do things and it would just happen. And now when you do things, you sit there and you wait for things to happen. Okay, and so scalability is awfully important. Okay, some other reasons are that it provides, algorithms provide a language for talking about performance. So when you talk about an order n squared algorithm, people know what you mean because they've studied algorithms. Okay, and they know how that compares to an order n log n algorithm. Okay, we'll talk about these notions. Another thing is that the lessons that we learn here generalize in a surprising number of ways to related fields. Okay? And finally, and this is my favorite reason, speed is fun. Okay? I mean, why do you think that, we have races, and the Olympics, right? We have car races and, have all the kinds of things, being on that cutting edge and making, the car races, for example, a good analogy, okay? All of the auto manufacturers, everybody who's involved in automobile manufacturing gets involved in those car races. Now, I'm not a car racing fan particularly, okay? But it's amazing how much effort goes into that, and it's amazing how many new technologies come out of that effort of being on the cutting edge, okay? And so speed is lots of fun. I go, whenever I drive under the speed limit, okay? Okay, but I know that the speed limit is not what's posted, but what they ticket you for. And I don't know why it's fun. I like to ski downhill, I like, there's just lots of things. I like to run, speed is fun. Okay, it's woo, we go. So that's why I do this. This is good stuff. Okay, so that's sort of a basic reason that we're going to do what we're going to do this term. Okay, there are lots of good reasons. And the other thing is that for some problems, by the way, performance is the most important thing. Okay, there are critical problems in science and engineering where performance is far more important than anything else. And there's some good examples like doing quantum chromodynamic simulations. Performance is the only thing that matters there, and they are willing to invest huge numbers of people doing all kinds of crazy things in order to get better performance on their codes. Okay? Because then they can understand how the universe is made a lot better. Okay, we're going to start out here by looking at the problem of sorting, which is a very simple problem, and it's a very old problem. Okay, we're going to study this problem for several weeks. Sorting is important. It's important you know the different types of sorting but mostly what we're going to get out of this is an appreciation of many different techniques in algorithm design. Okay, so we're both going to do the sorting algorithms, and you're responsible for understanding what those algorithms are and so forth. But really, it's the techniques that we're after, because we're going to see those techniques over and over again during the term. So this problem is a fairly simple one. We're given as an input a sequence A1, A2, AN of numbers. And our goal is to write a program to output a permutation of these numbers, A1 prime, A2 prime, AN prime. Okay, so a rearrangement of these numbers such that, that's my shorthand for such that, okay, such that A1 prime is less than or equal to A2 prime all the way up to A sub n prime. Okay, they're in order. Okay, very simple problem. So I'm going to start out with a very simple algorithm to solve this. It's an algorithm called insertion sort. Okay. And I'm going to write it as having two parameters, a and n, where a is the array that I'm going to sort the elements in, and n is the number of elements. Now, in practice, you would have this all packed into an object, typically, okay, when you're doing sorting. But what I'm going to write up is basically the thing so that it makes it easy to understand what the program is doing. I'm not going to be writing programs. And what we call the stuff here that I'm going to be writing is we call this all pseudocode. And pseudocode is basically allows me to do things like using the very ancient and descriptive language called English to describe the program, rather than being forced to use a modern language like Java, which makes me be more precise than I need to be in order to communicate. Okay, so you'll see that we'll get a very compact description. And so we do a lot of stuff in pseudocode, and the nice thing about using pseudocode is it does allow me to do English when you and I understand that we could work out the details. We can be informal. So the code looks like this. J gets 2 to n. So I'll write up the code and then we'll discuss it. Okay? So that's the code. Now you notice here that I haven't done things like use brackets or anything to, I've used indentation rather than braces or begin ends, okay? And the reason for that is I'm just trying to save how much is written down, and the pseudocode we use is designed to be compact. So in fact, there actually have been computer languages that use only indentation in order to group things, okay? Terrible idea. Terrible idea, because, you know, if the code goes from one page to the next, what matches up? Let me see. You know, it's just impossible to tell. You want braces, okay, in a real language. Okay, but for this, it's much easier, and it saves me a lot of writing to just be able to do indentation. We've tried to make this pseudocall so generic that anybody can do it. Another thing here, by the way, is that because we're studying algorithms, typically when you sort, you also have not just the value that you want to sort, there's also this other data you want to drag around with that value. That's called satellite data. Okay? But when we're discussing the algorithm, unless we are concerned with something having to do with satellite data, we'll just sort the numbers, presuming that you could, when you're actually programming this, you would worry about all these other concerns. So an algorithm is not dealing with all of the things you would be concerned with when you're programming it. I didn't make this into a nice object. Okay, I didn't worry about the satellite data and so forth. You still, once you have an algorithm for a problem, you still have some engineering to do. Okay, that involves you using all the skills that you're using in all your other courses. Okay? So let's take a look at what this does. It's always hard to understand something from pseudocode. And I don't want anybody thinking that they can give me a piece of pseudocode on a homework and that's a sufficient answer to a question. Okay? Normally you're expected to give an English description. And then also pseudocode if it's helpful to understand it. But certainly not necessary to give pseudocode. But it is necessary to give English. Okay? So it's also necessary for any code that you give to give a picture. Okay? Because you can always come up with a picture for what's going on. So here we have an array A. And in the outer loop we have an index J that goes from 2 to n. Okay, so let's say J is here. In order to understand programs with loops, there's a very important technique that we'll be talking more in recitation on Friday about, called the method of loop invariance. if you understand what is the same from iteration to iteration of the loop, you can not only understand what the program is, you can actually formally prove that this program does what it says it's going to do. And there are a lot of people who have worked on tools, theorem-proving tools, that will prove properties of programs. So in this case, the invariant that this outer loop maintains is that this part of the array is sorted. Okay? And it starts out by being sorted when we enter the program, because initially j is 1 before you enter the loop, essentially. Okay? And so one element is already sorted. And then we start j starting with 2, and now what we're going to do is make it so the first two things are sorted, and etc. So here we get to the jth step. Everything is sorted before it. And now what that innermost part of the loop does is it pulls the value of aj out into something it calls key. Okay, key gets a of j. And then it starts I out at j minus 1, and I marches this way through the inner loop. And at each point, it compares to see whether it is greater than or less than the key, or if it's hit the end of the array. And it marches down, and as it marches down, every time it finds something that's bigger than the value of aj, that is the value of key, it copies it up. And so it basically goes down doing this copying until it finds the place in the array where this goes, and then it copies it back. And then it goes to the next iteration of the loop. Does everybody see what's going on there? So let me do a quick illustration on a particular set of values. Okay, so we start out with something like this, and we start with j here. And we basically march down, and we say, oh, the 2 goes before the 8. Okay, and so then the array after we've made that change looks like this. And then we look at the 4. We say, oh, the 4 goes before the 8. So 2, 4, 8, 9, 3, 6. Now we look at the 9. And we say, oh, the 9 just stays where it is. Okay? 2. Now we look at the 3. The 3 goes all the way down to there. Okay? 4, 8, 9, 6. And finally the 6 goes in here. And we're all sorted. So we're done. Okay, any question about how this algorithm achieves its effect of sorting the array? Okay, fairly simple algorithm. Fairly simple algorithm. But we're interested in its performance. Okay? Its running time is the measure we're going to be using. And I want to stress again, although in this class we'll be focusing predominantly on running time, in practice there are a huge number of other measures we care about. How much disk storage it's using, how many accesses it makes to a remote site might be a measure that we care about. And all of the things that we ever are worried about in terms of resources, okay, are part of the domain of algorithms and part of what you use algorithmic technology to understand. So if I say, what's the running time in this algorithm? Well, it depends. Okay? Depends upon what we run it on. Okay? Depends on the input. Okay? In what way does it depend on the input? You've already answered once. How about somebody who hasn't raised his hand? There we go. Is the input comparable? Well, it is. It's a set of numbers. Okay? It's a set of numbers. But it does depend. I mean, notice that in this I never checked to see that it was a set of numbers. Okay, another thing that you want to do when you write code is always check your inputs. Okay, make sure they're proper and so forth. Didn't bother to do that because I'm just interested in the essential sort of intelligence of the code. Okay, not all the other stuff that we do as a matter of engineering practice and makes it easy to debug and so forth. Somebody had a... Yeah, the number of iterations in the inner loop can change. For example, this one would take longer in a computer, which is doing one thing at a time, essentially, okay, than this one, where it could just insert it directly. Okay? So when is this algorithm going to run really fast? If it's already sorted. And when is it going to run really slow? Yeah, reverse sorted. Good. Okay, good. So the running time depends on the input. Okay, what does the input actually look like? Okay. For example, if it's already sorted, in this case, then it's going to run a lot faster than if it was reverse sorted, in which case you're going to have to run down to the end for every single one. Okay? It also depends, and this is something that is actually a simple but a key, is the running time depends on n. Depends on how many things we're sorting. If I'm just sorting a few things, it'll run fast. Okay? If I sort a large number of things, it's going to be slower. Okay? So it depends on the input size. So for example, if we're sorting 6 elements, as I did in this example, versus, say, 6 times 10 to the 6th. Okay? 6 million elements take a little longer. So we tend, when we do our analyses, we tend, as a consequence of the second one, to parameterize it in the input size. Okay, when we do our analysis, we want to know how does it behave essentially as a function of n. What's the program behave like as a function of n? Okay? And generally, we want some type of upper bound on performance. Okay? Because an upper bound represents a guarantee to users. Now, it's not always necessary that you have a guarantee for your users. But if somebody comes and says, well, you're going to run my code, and I promise you it will always be fast, versus you're going to run my code, and sometimes you're going to have to wait until next year before it's complete. Okay? But sometimes it works well. You're going to prefer the guarantee. Just like when somebody says, here's a code, and it sorts numbers usually. Sometimes it doesn't quite sort them. Okay, you're not interested in that routine, right? For correctness purposes. It doesn't always sort it, and you're interested in a sorting routine. The fact that it doesn't always sort it, okay, so what do you have after it's not sorted? Why did I bother calling this routine and spending time executing it? No. So performance, it's not as strong a case that you need a guarantee as it is for correctness, for example. But it's a guarantee. You want to try to guarantee things about the code that you write. Okay? So let's analyze. So first, let's talk, before we do any analysis, let's talk about the different kinds of analysis that we're going to see in this class. Where we're going to get upper bounds. The most common one that we're going to get is is called worst case analysis. And this is what we're usually going to do. Okay? So this basically says, let's look at, of all the inputs we could possibly feed this program of a given size, that is of size n, say, in the sorting case, what's the longest it would ever take? Because if we can put an upper bound on that, then we have an upper bound on its running time for any input, because that's the worst one. So in that case, we'll say that in worst case analysis, we say T of n is the maximum time on any input of size n. Okay? And so T of n is a function now. Okay? Now, the maximum time, okay, if I didn't say maximum here, I say T of n is the time on any input of size n. T of n is not a function. It's a relation, even though I've written it like a function. Okay, because the time will vary depending upon n. And there are other cases that we're going to see where there are programs that even for a fixed input will have varying running times. Randomized algorithm is an example of that. An algorithm that conceptually flips coins as it executes. Okay, and the running time can depend on those coin flips. Okay, so it's very important to understand that this becomes a function when we put the word max there. Okay, if you don't have the word max, then it's just a relation. And we don't have a definite time. Even though we could talk about it that way, it wouldn't be a definite number. Okay? The next one we'll see often is average case. Okay? And we're going to do this sometimes. Okay? In this case, we say T of n is the expected time over all inputs of size n. Okay? Now, what do I need in order for this to actually be well-defined definition? I'm not done with the definition at this point for average case, for T of n in this case. What's missing here? What's missing? When I say expected time over all inputs of size n, well, first of all, for sorting, if I'm doing numbers, how many inputs of size n are there? An infinite number. There are an infinite number of numbers. Okay, so that's not particularly well defined. Okay, I guess that's even, okay, that is, if I'm going to take the expected time over all inputs, I got to worry about that. But in fact, it turns out that the actual values of the numbers doesn't matter in that code. If you look at it, the only thing that matters is their relative order. Okay, so how many different permutations? So there's really only n factorial different permutations of numbers that I could put in there. Okay, but even so, there's another issue that's very important. Whenever you talk about probability and computing expected time, what do you have to know here? This is 6042 material for MIT students. Okay.
That all inputs are equally likely?
Well, they might not be equally likely, but you're on the right track. What do you have to know? Sort of. The equally likely was closer. Okay. Variance? Yeah, you need to know the probability of a given input. In other words, what's called the probability distribution. And one such distribution is that all inputs are equally likely. That's not I've never seen a case where that actually happens in practice. Almost always when people do sorting, most of the time it's almost already sorted. Okay? It's like they're sorting bank checks. What order do the numbers of bank checks come in? Well, they're not out, they may be out of order a little bit, but they're not. It's amazing how often when people sort, the thing they're sorting is already almost sorted. Okay, so, but the important thing to do is you need, if you're going to talk about expected time, you need some assumption of a probability distribution, some statistical distribution. Otherwise, it makes no sense to talk about expected time because you don't know the probability of an input. Okay? You've got to know. So I don't want anybody saying I'm doing expected time and assume that they know what the distribution is, because if you violate this assumption, this analysis isn't going to make any sense, okay, in practice. And you may see cases where different types of inputs, you get different probability distributions. Okay. The third one that we're going to talk about is best case analysis. Okay? In other words, what's the best this ever does on an input? Okay? So this is generally, for getting upper bounds, this is bogus. Okay, and yet you see it in computer magazines and things. Oh, I have this algorithm, and its best case is. Why is this a bogus notion? Why is this a lousy notion of computing? Yeah?
Your perception of how well the algorithm would perform in the average case is typically would be way, way better. Because the best case would be way better
than the way it averaged, yeah. And in particular, it's not just that, but if you think of it as a social interaction type of thing, suppose that we say we're going to have two companies make their codes, and one of them, and we're going to measure the two companies on their best case, sorting algorithm. Okay? So then, what does that mean? What are you comparing for the two companies? You're saying each company can come up with a single input which runs faster than the other single input that these other guys have out of all the n factorial inputs, the different permutations that you might try to sort for a problem of size n, okay, then that guy wins. And it doesn't matter how it performs on the other n factorial minus 1 permutations. Okay, that's really bogus. Okay, here at least you're saying if it's the maximum time, at least now since you're getting an upper bound, you're bounding everything. Here you're bounding 1. Okay? In particular, I can always take any slow algorithm to solve a problem. And the first thing I'll do when I enter the slow algorithm is I'll check, is this an input, a particular input for which I know the answer? And if it is, I'll say, print the answer. Okay, and so now I've solved it for one problem, and I've got a great best case. And yet my algorithm, who cares what it does on the other inputs? So it's cheating. Okay, so whenever anybody talks to you about best case analysis as a means of upper bounding things, it's a bogus notion. It's a bogus notion. You should all be able to identify it as a bogus notion. Okay, that person is a charlatan and should be dealt with the way we deal with charlatans. Namely, we elect them to the Senate or whatever. Okay, so here you can cheat with slow algorithms, with a slow algorithm that works fast on some input. Okay? This is just a cheating idea. So we don't deal with best case analysis. Now it turns out best case analysis is worthwhile if you're looking at lower bounds. Okay? How do you say that an algorithm is taking at most some amount of time? But in fact, most of the time we still care about what the lower bound is on the worst case. We want to know that in the worst case it takes a certain amount of time. Moving right along here. Okay, let's analyze insertion sort. Fortunately, insertion sort has a fairly simple analysis. Okay, start simple. Okay. Actually, let me toss this up in case people didn't catch that last piece. Okay. So insertion sort analysis. So the worst case we discussed was when? Reverse sorted, right? Input reverse sorted. Okay? So in that case, every time we go down the list here, we're going to be going all the way to the end. Okay? And so the number of iterations, the distance we're going to go for each inside this loop, the number of values that I will take on, okay, is going to be proportional to j. So we're first going to basically do essentially something proportional each time proportional to j, and j keeps increasing. So the time is then going to be the sum from j equals 2 to n of something proportional to j. Okay? So what is the... So everybody knows theta notation? Okay? We'll talk about theta notation in a moment. I skipped a page. Very nice. Okay. I skipped a page. How are we doing on time? We'll get back to this, okay? Because there are a couple of other things that I want to talk about in insertion sort. We'll get back to this in a minute. Okay, so for insertion sort, okay, when we say what is the worst case time, okay, we still have some things to elaborate here in terms of what we mean by time. Okay, because the time that a program takes, as I think most of you are aware, depends upon what computer you run it on. If you run it on Athena, it takes a long time. Okay, you run it on your latest laptop, whoa, did that go fast. Okay, so it depends on the computer. Oh my gosh. So many complications. What's great about, and it depends on two things in the computer. One is in the relative speed for comparing algorithms. We might just be concerned about the relative speed. We'll say, well, let's assume that we run two programs on the same machine. Okay, and then we'll compare them. That makes sense. Okay, so this is on the same machine. Okay, and the other thing is the absolute speed. This is on different machines. Both of these are sort of, the relative speed will be fine if I'm just looking on one computer, but notice that even in this case, I have some issues to deal with because it depends upon the relative speed of the different primitive operations that the computer is capable of. What's its memory access speed? How fast is its CPU to do a multiplication versus doing an addition? Okay, versus adding 1. Okay, and so forth. And all of those are just like a huge number of different things you have to worry about in order to get the absolute performance. Okay, and so this is where the field of algorithms back in the 60s made a huge advance. Okay, and that was because people, when they were writing up their algorithms in the early days, if you go back and you look at some papers in the 1960s and late 50s, you discover that they say, well, we ran this program to do the sorting problem on this machine, and here are the running times we got. And somebody else, he doesn't have that same machine. Even if he has the same machine, he may have a different way of doing it. And people say, well, but we're really interested in knowing whether the program is good. We're not really interested in the details of that machine, whether its multiplier is 20% faster than the other guy's multiplier. Okay? And back in those days, multiplication, by the way, was done in software. Okay? Not in hardware. Okay? So then you're worried about your multiplication algorithm as well. Okay? So, boy, that made it really hard to compare algorithms. But there was this great big idea that came along. Actually, capital I idea, I'll say. Big idea. And that was something called asymptotic analysis. This is a huge idea. Huge. Okay? And the first thing is it says something that looks patently stupid. Okay? They say you're interested in the time of your algorithm. Okay? First thing to do is ignore all machine-dependent constants. How fast your multiplier is, how fast it takes to add, what your memory reference time is. I thought we were interested in performance. All those things contribute to performance. But that's the first step. Ignore machine-dependent constants. Completely ridiculous. Okay? But there's a reason for that. What we're going to do is, rather than looking at so closely at the running time in, down to the nearest picosecond, okay, we're going to look at the growth of the function t of n, the growth of the running time as n gets large. Okay. And so we get asymptotic analysis as a major analytical tool in computer science. Okay? And the basic idea is to use theta notation. So people remember theta notation. I knew I had this in my notes. Okay. So what's theta notation? Well, if you're a mathematician, you know that definition of what theta is. Right? Theta is the set, theta of f of n is the set of g of n such that, et cetera, et cetera. There's constants and bounds and stuff like that. And all of you have learned that, I hope. Okay? But we know from an engineering point of view there's an easier way of dealing with theta notation, right? What do? You don't have to exercise that definition every time I give you a polynomial or something to say what is it theta of. What do we do? Yeah, throw away all the lower order terms and focus on the most significant term, and throw away the constant out in front too. Okay, so we just drop low order terms, ignore the leading constants, okay, that's the engineering definition. So for example, 3n cubed plus 90n squared minus 5n plus 6046 is theta of n cubed. Okay? And why is this a good idea to do? Well, the constants, the machines themselves are only going to influence the constants, generally. Okay? That's all they're influencing. They're not generally influencing the size of your input and so forth. And so, if we can compare two algorithms and look at its order of growth, if I have something with a slower order of growth, eventually it's going to beat, for large enough input, it's going to beat something that has a higher order of growth. Okay, so if we draw a picture for this, I think I can get rid of this. Okay. So if T of n here mapped across n here. Okay. So I'll have one algorithm that has a running time, worst case running time, say, of this. Okay. And I'll have another one that, say, has a running time like this. In asymptotic analysis, if this growth rate is faster than this growth rate, then this one's going to be better after some point. Even if I take a bad algorithm and run it on a fast machine and a good algorithm on a slow machine, okay, the good algorithm is eventually going to beat the bad algorithm for a large enough input. Okay, and this, by the way, you see this all the time. Somebody says, instead of using that huge supercomputer on my PC, I can do this thing that was taking all those people with their huge computers to do. Why is that? He's got a better algorithm. Okay? And so algorithms are hugely important technology. And as n gets large, we're always interested in this. Now, the thing I don't want anybody in this room, if you are going to be a competent engineer, to think is that the constants don't matter. Constants do matter. They matter, for example, when you have two algorithms with the same asymptotic performance. Okay? They matter if your algorithms are running in this range before one has dominated the other. And so the sorts of things we won't do this introductory class particularly is looking at things like where are crossover points. All of these are enormously important in practice. But still, you can structure the problem. Okay? And as we'll see, there are algorithms for sorting where n naught is something like sorting of 30 elements. Okay, we'll see that. So you always have engineering design trade-offs to do in practice. Okay? But asymptotic analysis will help to structure your thinking. Okay? But it doesn't mean that just because something is a theoretically more efficient algorithm that it's really better in a particular practical situation. Okay? So you have to be an engineer still. Okay? Doing asymptotic analysis is not the end of the story. You still have to be an engineer. Okay, how are we doing on time? So we got started a little bit late, so I hope we can get this this done without going over too much. I'm really sorry that it got started a little bit late. So insertion sort analysis, what we just did before. Okay, so T of n is then the sum, j equals 2 to n of theta of j, which is theta of n squared. Okay, why is that? So we did this part before. We said it was theta of j. This is the part I erased when I realized I had skipped over one page of lecture notes. Okay, why is this theta n squared? What's the basic mathematical justification?
Because the sum from 1 to n inclusive is of n times n plus 1 over 2, so that's about n squared.
And so what's that rule? There's a general name for that. Okay, it's a type of series. Arithmetic series. Good. Okay, this is an arithmetic series. So everybody should know how to do arithmetic series because we've just seen a good application of one. We were able to analyze that in the worst case, okay, insertion sort runs in n squared time. What does it run in the best case, by the way? Even though we're not going to care too much about that analysis, but it'll tell us something about the algorithm. It's order n because then the inner loop, okay, whatever's going on inside here is only going once through that. and however many times, if it's not dependent on the input size n, it's a constant. That's what we mean by something being a constant. It's independent. Its time is independent of the input parameter. If it's independent of the input parameter, it's constant. So then it's theta 1, and then we would get theta n. So a fairly good range between n and n squared is the growth. So insertion sort, you can see running very fast and very slow, depending upon the input. And the point is that the growth changes. Okay, the growth. Yes?
Does that mean it should be bigger than square?
No, because this is theta is used to bound the function for t. T is a function. It's the worst case time. Now sometimes you'll see people who treat t as a relation on running time. They'll say t of n is O of n, but that doesn't say that of O of n squared. But if it's O of n squared, it could also be O of n, and we wouldn't know the difference. Okay, because O is just an upper bound. So theta is saying that this is both upper and lower bound on the worst case running time. Okay, so you've got to distinguish between whether you're talking about the function or talking about the algorithm. The algorithm running time may vary, but the worst case running time we can talk about with theta. Okay? Average case. So this is the worst case. Worst case. Okay? So the average case. Oops. Okay? For the average case, t of n is equal to, well, how far on average are we going to run down this list to insert a new element? We have a new element. It's basically a random element. We have a sorted array that's running down to put itself in. How far does it go down? Halfway. Why halfway?
Because there's an equal likelihood the number could be greater or lesser.
Yeah, there's basically an equal likelihood. It's basically an issue of, if you think about it, of linearity of expectation. Okay? So probability coming in. Okay? So we go about halfway down. So it goes j equals 2 to n of theta of j over 2. And what's that equal to? That's still order n squared. That constant doesn't matter. And this is a fact that we often see, that is that the average case is often not much better than the worst case. For some problems, the average case is much, much better, and we'll see examples of those too. Okay? But for many problems, whether you did average case or worst case, you're in the same order. A random input is almost as bad as a worst case input. Okay? It doesn't vary by more than a constant factor as n gets large in the running time. So is insertion sort fast? Actually, there's no simple answer to this. The actual fact is that it is moderately fast algorithm for small n. It is a good way of sorting things if you have a small number of them. Okay? But it turns out it's not at all for large n. So how fast can we sort? Who knows something about sorting? Somebody in the back here. Too many front pair. Oh, you haven't answered yet. N log n, yeah. So let's take a look at an algorithm that does that. I'm sorry, as I say, that we got started late. But I don't have any choice but to continue so that the Singaporeans can get the full lecture. But it will be up on the web if people need to leave early. Or leave on time, I guess. Okay? So merge sort. Is one such algorithm. And here I'm going to do a different type of pseudocode. We're merge sorting the array A of 1 to n. And this is going to be very English type 1. So if n equals 1, we're done. We can sort a one-element array pretty easily. Okay? And then we can recursively sort the first half of the array, 1 up to ceiling of n over 2. Okay? And the second half of the array, ceiling of n over 2 plus 1 up to n. Okay? So we recursively sort the 2 halves, and then we merge the 2 sorted lists. Okay? And the key subroutine that we use is a merge subroutine, and let me show you how that works. Could one of the TAs stand outside and just guard us and let them know that we've unfortunately are running over with a videotaped lecture if anybody comes for the next class? Okay. So let's merge these 2 lists. Okay. So the basic idea of the merge is that if these 2 lists are sorted, where's the smallest value? It's going to be at the head of one of these lists. So let's look at the 2 elements and see which one's smaller and output it. Okay? So we get 1. And then what we do is we erase that element. And we look at the new 2 heads of the elements, which is smaller, the 2. We put that out. And then we erase it. And now we look at these 2, and that one's smaller. Okay? So we just keep going through erasing and comparing, and always output the smaller of 2 elements. Okay? So how long does it take me to merge a total of n elements there? Asymptotically. Yeah, it takes order n time, okay, on n total elements. Okay, because I'm just doing a constant amount of work. It has nothing to do with the input size for every element that I output. And when I output them all, I'm done. Okay? So that's a theta n time. So we can actually now write, okay, the running time of this recursive program as a recurrence. Okay, so if t of n is the time for merge sort, then how much time do I spend on this statement number 1? Close that door, please, somebody. TA, so that because it's very noisy, it's hard to. Okay. So how much time do we spend on statement number 1? Okay, theta 1. Now that's actually an abuse. That's true, but it's an abuse. Okay, because there's nothing that is approaching infinity here. Okay, but we're still going to use the notation theta 1 to mean a constant. It's an abuse, but it's an acceptable abuse. How much on this one? No. To recursively sort 2 sublists. Excuse me? No, you're thinking too hard. It's an easier answer than that. You're thinking. Yeah, it's twice. It's actually t of ceiling of n over 2 plus t of floor of n over 2. That's how many are in the second one. So it's really, I'm going to write it and be sloppy here because it turns out it doesn't really matter in the asymptotic solution. Okay, so that's a bit of sloppiness that I've done. Okay, and then it takes how long to merge? We just analyzed that. Theta of n. Okay, and so what that gives us is a recurrence for the solution. T of n is equal to, now in this recurrence, we generally don't bother to write the initial conditions, because for running times of algorithms on a constant number of inputs, it only takes a constant time because there's nothing growing there. So we don't bother to write it, and as we'll see, the only reason we get away with that is because it doesn't affect the asymptotic performance. So we'll just simply write T of n is 2t of n over 2 plus theta of n. Okay? And this has a solution, theta n log n. Okay? And I'm not going to spend the time to go through that. I was planning to, but we got started late, unfortunately. Now, I'd like to draw a couple of conclusions, and then we'll be done. So this theta n log n grows more slowly than the theta n squared for insertion sort. So therefore, we can conclude that merge sort asymptotically beats insertion sort in the worst case. Okay? It's a better algorithm for large enough inputs. And in practice, if you actually sit down and code this, it tends to beat it for merge sort beats insertion sorts for about n bigger than 30 elements or so, depending upon your machine. Okay? And let me encourage you to go try it out. Neither of these things is hard to code up, and you can be very impressed with, even on a fast machine, how slow insertion sort is, and even on a slow machine, how fast in comparison merge sort is. Thank you very much.